Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 24, 2026, just 5 days ago. It introduces Actor-Curator, a framework that secures relative performance gains of about 29% on AME 2024 and over 30% on ARC-1D by treating data selection as a learning problem. The paper is titled Actor-Curator County Adaptive Curriculum Learning via Policy Improvement Bandits for RL Post-Training. And as we'll see later, the sheer efficiency of this approach, with up to 80% speed-ups, is really quite remarkable. So Figure 1 maps out the co-adaptive training loop. First, at Step 1, a neural curator selects specific problems from a large bank instead of using uniform sampling. Next, in Step 2, the actor trains on these chosen problems and updates its policy. Finally, Step 3 closes the loop. The system measures the actor's performance gain and uses that improvement as a reward to update the curator, allowing it to learn exactly which problems drive the most progress. While the concept is simple, Figure 2 details the mechanics. On the left, a candidate batch is pulled from the problem bank. The curator assigns probabilities to these candidates, filtering for the most promising tasks. After the actor trains on this selection, the system compares the old and new policies to measure the performance gain. Since only chosen problems provide feedback, this partial signal is used to update the curator on the right, teaching it to better predict value next time. Alright, with the mechanics clear, Table 1 presents the main performance results. It compares Actor-Curator against uniform sampling and strong curriculum baselines across benchmarks like Countdown and ARC-1D. The standout is the performance on harder tasks. On ARC-1D, the method achieves a relative improvement of over 30%. On the ARC-hard subset, that gain jumps to nearly 59%. Similarly, on AME 2024, it secures about a 29% boost, proving adaptive curation excels at difficult problems. Well, while Table 1 listed the final scores, Figure 3 reveals the actual training dynamics. These plots track test accuracy over time for Countdown, Zebra, and ARC-1D. Look at the Countdown panel on the left. The purple Actor-Curator line rises much faster than the light green uniform sampling line. This trend repeats in the Zebra and ARC-1D charts, showing that the model does not just end up better, but learns significantly more efficiently. By focusing on high-value problems early, the framework achieves top-tier performance in far fewer steps. So Figure 3 showed us the speed-up. Now Figure 5 reveals the underlying strategy by tracking problem difficulty over time. Across tasks like Countdown and Math, the green dashed line marks the average difficulty if we just sampled randomly. The blue line, however, tracks the curator's actual choices. Notice how in the Countdown and Math panels, the difficulty starts near the average, but climbs steadily as training progresses. This confirms that the system naturally discovers an easy-to-hard curriculum, feeding the actor more complex challenges only as it becomes ready to handle them. Alright, while Figure 5 showed the curriculum strategy, Figure 7 validates the system's robustness through 3 ablation studies. In Panel A on the left, we see that Actor-Curator works seamlessly with other update algorithms like GRPO, maintaining a massive lead over uniform sampling. Panel B in the center compares different scoring objectives, proving that the proposed policy improvement target outperforms simpler heuristics like regression. Finally, Panel C on the right is particularly interesting because it shows that varying the curator's size from 0.6 billion to 4 billion parameters makes almost no difference. This implies you can use a very small, efficient model as the curator without sacrificing performance. Okay, having established robustness, Table 4 lists the peak validation performance achieved within just the first 100 training steps. This detailed breakdown confirms that the efficiency gains hold across different model architectures, specifically QN 2.5 and Llama 3.2. If you look at the columns for uniform, SEC, and PCL, the Actor-Curator method, labeled AC, consistently scores higher. The improvement column on the far right highlights the magnitude of these wins, particularly on ARC-hard and AIM-24, demonstrating that the curator identifies high-value problems almost immediately. Wrapping up, 2 takeaways stand out. Actor-Curator proves that data selection is a learning problem, not just a static pre-processing step. By automating this with a co-adaptive bandit framework, we see massive efficiency gains and stronger reasoning performance without human annotations. This points toward a future where models actively choose their own curriculum. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.